Yeah, sounds great. At least I'm assuming it is. Just a second. Let's get this thing going. Hi, everybody. Thanks for staying awake for my talk. Here, full screen. That'll do it. All right. I am digging a bit. What are my limits before I go off the thing? There we go. That's good. Yeah, that's right. All right. All right. Well, thanks everyone for coming today. My name is Brent Cook. I work at Rapid7. I'm the manager for Metasploit. What does a Metasploit manager do? Well, he does a little bit of everything, but I actually get the code as well, so it's kind of a neat thing. And today I'm going to be talking about some code that I wrote with some other people as well. And basically the idea of this talk is it's about building a universal Meterpreter payload. And we're going to be talking a little bit about the hows, the whys, the whats, what we basically did to make something that would run anywhere, work anywhere, and allow people to exploit things anywhere they are. So for this talk, I'm going to make a little bit of assumptions. I gave a talk on C programming not too long ago at Austin B-Sides, and I probably didn't make this super clear, but if you know C, that's actually a really great thing, because I'm going to be showing some C code. If you don't, I will definitely be explaining it and sort of going through like what we're doing here. If you know a little bit of Ruby, because we're going to talk a little bit about Metasploit, it's okay. You don't have to know a whole lot of Ruby for this. We're going to talk a little bit about makefiles and things like that stuff too, and that's very exciting. So if you've ever built any kind of software, you might have used a makefile before. If you know a little bit about an operating system, it's also really nice to kind of know a little about like what a system call is, what a library is, that sort of thing. And we're going to talk a little bit about exploitation, but not a whole lot. Mostly we're going to talk about software engineering and fun. Let's see, wrong way. So just a little bit about myself. I am not traditionally an offensive security guy. I worked in embedded systems for a long time, worked on networking stacks, worked on firmware, U-boot porting, Linux kernel drivers, all that sort of thing. In fact, that's where I first got exposed to Metasploit. I worked at Breaking Point Systems, and I worked with H.D. Moore. We were the first two employees at that company, and he worked on the security side, and I worked on custom hardware to make security go faster. So we kind of were a team. I didn't know much about Metasploit. I remember when I first got introduced to HD, it's like, hey, it's HD Moore. I was like, hi. All right, cool. So it was kind of interesting. Everyone was kind of like agog. Well, all right. So anyway, so about 10 years later, HD actually convinced me to come to Rapid7, and I did my first Metasploit pull request. Oh, I know what's wrong. I'm chinning the microphone. Let's see if I can avoid that. There we go. And then a month later, after I started working at Rapid7, I broke the whole Metasploit tree. But hey, you learn through experience, right? I also work on LibreSSL and an OpenBSD committer as well. So a lot of different open source projects and a lot of different things. I'll talk a little bit about how that kind of has shaped some of the things I've done as far as work for Metasploit as well. Main motivation. Actually, this is the main reason why I even came to Rapid7. Todd Beardsley, who was heading up the Metasploit team at the time, basically wanted to run Meterpreter on everything. We're looking at IoT, we're looking at routers, looking at phones, looking at switches, all this kind of stuff. That was suddenly had an IP address. You want to be able to run Meterpreter on it. Sure, reverse shell is fun, but you can only get so far a lot of times with BusyBox, and it's nice to be able to have the ability to do pivoting and take pictures and do all kinds of different interesting stuff. So that's basically the idea here, is that we wanted to run Meterpreter on all things. Of course, if you write exploits, it's not that much fun if all you get is a reverse shell. When we started looking more closely into sort of the world of embedded exploitation and sort of exploiting things beyond just the standard Windows boxes, we found that there are a lot of interesting sort of things to overcome. Sandboxing is a real thing. Like SE Linux does a pretty good job of restricting what you can do. Other systems like Android and iOS, they do a lot to prevent malicious processes from doing weird things. Like, for instance, you can't fork if you're in iOS. There's a lot of interesting stuff that you have to work around. Of course, there's also memory and disk and CPU constraints as well. When you want to write a payload that runs on, like, say, an XScale processor from 2004 because you want to pop a router or something like that, it's very useful to be able to be a lightweight. If you want to inject into a switch, those things are tuned to run exactly the payload or the exact load that they're designed for. So you don't necessarily knock over someone's switch just because you inject an interpreter into it. Another reason why we basically want to take under this project is Traditionally, a lot of the interpreter payloads for non-Windows systems have been ported straight from Windows. And what we kind of found was that it's very difficult actually to get a kind of a sane API when you port from Windows to other systems versus going from other systems to Windows. And I'll give you guys some examples of some interesting things we've run into with the other model. So how do you start a project like this? I want to write an interpreter that runs everywhere. Well, I want to talk a little bit about another project that you should certainly check out if you watch YouTube. There's a great project called the Giant Robot Spider Project. And basically the idea behind this project was the guy, an inventor, wanted to basically build a giant robot spider that he could ride. Obviously, what do you guys think you should do when you want to build a big project like this? What's the first step? Obviously, you need to cut down trees, build a sawmill, and use the lumber from the sawmill to build a workshop. Because obviously, you can't build a robot spider if you don't have a workshop. So actually, the guy goes through 100 different videos. And the first thing he does is actually he's building all the infrastructure he needs in order to build the raw materials that he then uses to build the robot spider. He eventually gets to the point where he builds a robot spider, but along the process he actually raises the whole family. Just a whole bunch of other things happen to him, and it's kind of an adventure until itself. Obviously, if you want to actually ship a software, that may not be the best way to go, sort of starting from the very beginning, although it's sure to be very fun and entertaining. But certainly, definitely, Jamie Mansell is the guy's name. If you want to check him out, it's a very cool project, and there's some good summary videos too. But let's take sort of an inventory of what we have here to actually build this universal interpreter. So, if any of you guys Metasploit users, have you ever used Metasploit? Got a few guys out there, and so you guys have used Meterpreter, and have you guys looked at how it actually works, under the covers, or you just kind of inject? All right, got one in the back. All right, so this will be totally boring. I apologize. Well, basically, the idea behind Meterpreter is it is sort of a way to abstract the OS from an exploiter's point of view. Meterpreter provides a lot of interesting things. One is, of course, it provides sort of a stable base core set of APIs called the core API. This basically doesn't really do a whole lot. All it does is connect to Metasploit and says, I'm here, and here's what I know how to do. It's kind of like in a language being able to do reflection, where you can sort of basically ask, what's available? What can you actually do that I could use as part of an exploit or a post-exploitation scenario? Of course, we have a whole lot of extensions as well. So, for instance, to do anything interesting like open a file or do something on the network, open up a tunnel, this requires extensions. And so we have extensions like the standard API, which is all the stuff that every Meterpreter supports. We have the extra API or Ext API, which does things like privilege raising and other stuff like that, changes file system parameters. And then there's a whole bunch of other APIs and extensions built on top of that you can add for specific purposes. Like, for instance, on Android phones, we have a specific Android API that allows you to do Android things like tracking GPS and that sort of thing. We also have a transport, which is basically how does the Meterpreter talk back to Metasploit. This can, the outer transport is designed to look obfuscated, so you can't really tell what the traffic is, like it's HTTP. You can theoretically embed it into any other kind of network protocol as well. And if we get some time, we'll talk a little bit about that. And then under the covers, there's a protocol called the creatively named TLV protocol. Actually, it's not TLV; it's actually VTL. Basically, it's where you encode the length and the type and the value of a command into a packet, and that basically is a low-level primitive that everything in Meterpreters uses. And of course, we also have modules that run on Metasploit itself, and these basically tell Meterpreter what to do. It's sort of a list of instructions and call and responses. So we've got this sort of infrastructure, and with this infrastructure, we can build a Meterpreter that works like Windows Meterpreter. It basically follows the API. So what kind of Meterpreters do we have? Well, when I first started, we have 7 Meterpreters. Did you guys know that there were 7 Meterpreters? Not only 7 Meterpreters, we have 4 separate code bases that all implement basically the Meterpreter spec. We had 3 that were Windows-based, 32-bit, 64-bit, and a Linux 32-bit one that kind of worked, but not really. We have Android and Java, which Java before Java apps, desktop, that sort of thing. Python and PHP. Now, Python and PHP are very interesting in that you might ask, well, if you have native ones, why do you need ones written in Python and PHP? It really depends on this exploitation scenario. For instance, you may be on a system where you don't have something that matches the underlying architecture. Maybe it's ARM, maybe it's something else. You can, of course, also have apps that are cross-platform. So you can have an app that can run on Windows, can run on Linux, can run on OS X. And you want to be able to exploit it in basically the same way across all the different environments. Also, a lot of times, the method by which you inject the payload can change which payload you use. For instance, let's say you had some sort of a PHP deserialization bug in a web application. You might want to inject PHP Meterpreter because you can easily just encode it straight in and just deserialize it into an object and you get remote code execution. So there's a lot of reasons why you have these different interpreters. What I basically wanted to do was get rid of this guy here, Linux 32-bit, sorta, and make it something that was really good and well supported. Also, while we're looking at inventory, how many lines of code do we have? A lot. 677,000 lines of C code in Windows Meterpreter. That's a lot to maintain, and a lot of it comes from just kind of reinventing the wheel in a lot of places. Kind of everything's sort of written from scratch. A little old, a little bit of history and legacy there. How can we improve that? How can we reduce the amount of code that we have to maintain here to port things to new operating systems? All right, what are some other things that we have? I'm going to talk a little bit about what the code looked like within Windows Meterpreter. And when I was talking earlier, I was talking about Windows, porting from Windows to Linux is a lot harder than going from Linux to Windows. And the reason why that is because there are a lot of interesting structures within Windows that just don't have Linux equivalents. Like for instance, there's not really a such thing as an event handle, or even a handle in the first place. D-word doesn't quite make a lot of sense in Linux. And so you end up with all these sort of if not def Win32s where you sort of jam in a lot of different constructs that allow you to work within Linux. This kind of works, but there's some cases where you end up with things that just don't match very well. Like for instance, on Windows, a socket and a handle are the same size. On Linux, they're different sizes. So obviously you can't say an integer works for both of them. And in fact, that was one of the reasons why we weren't able to get 64 bits running on Linux for a long time. Was because we basically had this sort of fundamental type mismatch throughout the entire system. Obviously, you lose a lot of other data too when you sort of try to pretend that E and val, which is a POSIX error code, matches all these different Windows error codes. So we wanted to come up with something that would work more natively and then thus be more portable to a lot of different systems. To sort of give you kind of an idea about how this sort of macro cheating can be used in really weird ways. This is actually a picture of a Bourne shell code. If you guys ever used like a shell before, this is how the original Bourne shell worked, where basically the author didn't want to port it from APL. Instead, he basically wrote a bunch of macros. And this is actually C code. If you've seen C code before, you know that this is rather odd that you have like a rep and a per statement, and you have if and phi, and that's just because macros just really aren't a great way to write understandable code. So the obvious conclusion is, well, now we have 7 interpreters. Let's create an 8th one. Obviously, you reach that conclusion, right? But obviously, we should never do this. This is awful. This is an article from 2000, actually the year 2000, from Joel and Software. Now, since then, people kind of softened on this stance and thought, well, maybe you should rewrite software. But basically, I didn't want to create another Netscape 6.0 and basically work on this forever and never actually ship it because, again, 600,000 lines of code, how can I ever catch up with that? That's kind of crazy. So as Joel would say, this can be the single worst strategic mistake any software company can make. Well, not necessarily as, particularly a software company, but hey, if you just do it for fun, can it really be a mistake? All right, so why would we want another interpreter other than just like the code? All right, we want it to be smaller, we want it to be more portable, we want it to be more stable, which is a big problem if you ever used the old 32-bit Linux interpreter. You probably noticed it crashes really easily. We want it to be maintainable, but does anyone really need it? And here's what basically allowed us to find that need. Why did someone actually need it? I started working with Joshua Drake last year around this time, and he came up to me and said, hey, summer before, stage fright was a big thing. Everyone was worried about, oh, I just send a text message and I get full control of your Android device. And that was a great story. But the real reality behind it was Android actually had some pretty good mitigations. Even though you could run code directly within the media server process, it was actually pretty locked down in a lot of scenarios. SE Linux was turned on. You couldn't do a fork. You couldn't do an exit. You can't do a whole lot of things that you do with just your normal little bits of shell code where basically you spawn a reverse shell and you get a reverse prompt and you can do whatever. So basically, Josh said, I had to do like kernel exploits on top of this in order to get past SE Linux, and then it's not reliable, and I've got all this extra sort of hoopla to go through. I just want to be able to exploit stage fright, and how can I do it? How can you help me? And so what we basically came up with was like, how can we actually inject Meterpreter straight into the media server process and do it in such a way that we never have to actually fork anything, we never have to write anything to disk, and we never have to basically do all the things that SE Linux is looking for. So basically, how do we fly under the radar? And of course, this is going to be easy, right? Luckily, I've got some really smart people that work with me here, and obviously, porting software to a lot of different systems is really easy as well. In fact, this is actually a few things that I've ported software to in the past. Now, of course, past isn't necessarily going to indicate what the future will be like, but I was feeling kind of cocky and feeling like, hey, this will be easy. So talk a little bit about kind of one of my first efforts at building something like this. When I worked at Breaking Point, again, talking with HD and working with Metasploit, I worked at, we basically built our own custom hardware, and this is actually what the thing looked like. It's pretty cool. It's designed to sort of, at least people take notice of it in the data center. But it had PowerPC, it had ARM, it had x86, it had FPGAs, it had weird micro-coded CPUs, and we got it all to run under a single tool chain. Right? I don't know if you guys have ever built a tool chain before, but it can be really tricky, and back in those days you had to patch the heck out of GCC and libc and everything else. And so, it was kind of a good experience. And then moving on to, stop that. The modern world, 2005 was a long time ago, everything sort of moved on. But hey, look, there's this great tool chain out there called the Embedded Compiler Collection. It can build for Windows, for Mac, for Linux, everything. It'll work perfectly. Let's try for stage fright. And it didn't work. Why? Because to do exploitation, you have to do even more than just getting it to build. What do you need to actually build a payload that can actually be used for exploitation? And it's not just a matter of functionality, it's a matter of some other things. One, it has to be relocatable, meaning that the code has to be able to run anywhere within memory. You can't rely on the operating system putting it in the right place because you're basically subverting the operating system. You don't really know where you're going to be, when you're going to be. It needs to be self-contained. We want to make sure it can work on an old device from 10 years ago. We want to make sure it can work on modern things. If you ever built like some code for Linux, you know that if you build something on Ubuntu 16.04, it doesn't work on Ubuntu 14.04. That's because it builds in dependencies on the C library and other things. It needs to work on a lot of different architectures. You need to work on a lot of different kernels. If we want to write an Android exploit, every Android device is sort of a unicorn because every vendor's got a slightly different kernel, everyone's got a slightly different environment. How can we make something that's universal that works in all these environments? Well, let's talk a little bit about how we solve that same kind of problem when it comes to just shellcode. What I mean by shellcode would be oftentimes people write assembly language code that just does a few simple things like allocating some memory, writing some code into it, jumping to that memory, going forward, or maybe starting a socket, running a shell, doing some pipe redirection, and then connecting things together. What you normally want to do when you write shellcode is you want to also write it in a position-independent way because you don't know where it's going to be injected. You might have some sort of NOP sled that sort of runs into it, and it could be anywhere within memory. So you want to make sure it works in all different kinds of scenarios. But we don't want to write Meterpreter in hand-generated assembly code. Obviously, that's not going to work. So the solution here was position-independent executables. Now, typically, position-independent executables have the opposite problem in that they're not self-contained. They basically, if you've ever built like a shared library program, effectively that's position-independent. So if you've ever seen address space layout randomization, that's due to the fact that you have position-independent executables. How can we combine that with what's called static building, which is where you sort of glue everything together and you have all the dependencies built in? It turns out there was a solution. But before I get into the real solution, we'll talk about some of the prior art. So Windows Meterpreter has something called reflective DLL injection. This is something pioneered by Stephen Fewer about 7 years ago. And basically the idea here is that you have a little loader that loads, and it can actually sort of identify all the dependencies of a DLL and reflectively load all the dependencies into a target image. So basically doing all the things that the OS does, we do this directly inside the program during exploitation. Linux Meterpreter also had something really interesting in that it actually embedded a copy of the Android C library into itself and then zipped up libraries and then link them on the fly into the memory image. Pretty cool, but very limited to just the architectures we made it work on. What did we do to actually solve this problem? We actually found that someone had already solved it for us, but not because it was something that they wanted to do for exploitation. It was because something that allowed basically images to be built in a more secure fashion. So the idea normally with static images is that you just have all your dependencies linked together and they're all in fixed offsets. What if you were to take the shared loader, append it to a bunch of shared libraries, and sort of glue that all together into sort of something that looks like to the kernel, like it's a static image, but you really have it sort of relocate itself in memory. That's basically the way we've solved the problem, and we actually have a magical tool chain that does this all for us. But that's not quite enough. If we want to use something that's off the shelf, it assumes that it's actually running from the kernel. So basically, the Linux kernel actually did all the setup to get the payload running. How do we pretend that the Linux kernel is doing that without writing our own loader from scratch? The answer is, and I'm not sure if you guys can actually see this. Is it super tiny? Yeah, okay, yeah. So the answer here is, do you guys know much about how the Linux kernel loads a process? All right, so the idea here is that before the Linux kernel when it's setting up a process to run, basically it sets up what's called an initial stack. That stack contains all the stuff that the program needs to know how to run in its environment. Like for instance, if you type any command line arguments to a program, those will all be pushed onto the stack. So the stack will have how many arguments there are. It'll have a bunch of strings that point to each of the arguments. It'll also have a bunch of other things called the auxiliary vector. And of course the environment as well. A lot of different stuff gets pushed into the stack. But the auxiliary vector is interesting in that it contains things like where you should load. It also contains things like random number generators and other stuff like that. It's basically extra information you might want to pass to your program before it runs. What we do basically is we pretend that we are the Linux kernel in our shellcode. And we basically set up the stack exactly how the Linux kernel would do it. And by doing that, we're able to basically leverage existing compiler and loader infrastructure in a way that is now offensive rather than defensive. So it's pretty nifty. If you guys want to, afterwards, I can show you some of the code and exactly how it works. The other cool thing about this is that a lot of OSs use this exact same mechanism. Linux, every single BSD, OpenBSD, FreeBSD, NetBSD, AIX, HPUX, Solaris, they all use basically this exact same kind of stack infrastructure. Now, everyone requires a little bit of variation. Like, for instance, MIPS on Linux requires some extra things pushed onto the stack. But it's kind of a little bit of a trial and error. You can sort of figure out exactly what everything needs to work. And suddenly you have a universal loader that works on every Linux and potentially every other OS as well. Let's zoom back out. And again, like I said, a lot of people use ELF as a base format, which means if we target ELF, we get a lot of bang for the buck. In addition, this sort of static position independent executable mechanism, it's actually been OpenBSD since 5.7. So it's a great way to actually package portable shellcode, if you can actually exploit it, into OpenBSD if you really want to. A few other Linux distributions like Alpine Linux are based completely around this concept. Solaris doesn't even have static linking, so you can actually build just a normal program and it just works everywhere on Solaris. It's really great. And when it comes to like sort of the more obscure systems, sometimes we can load into memory, sometimes we can't. But in a lot of cases, it's one of those cases where you just don't care because no one's really monitoring the file systems on like some embedded ARM system. It's just kind of the fact of the matter. What are some other ways we can load things into memory? And this is stuff that we're working on as well to make this payload be able to inject pretty much anywhere. Mac OS X is kind of an interesting beast. There's a lot of stuff you have to do to sort of build your own loader and linker. But actually due to some innovations that have happened lately with OS X, it actually is getting easier to load things dynamically into memory. And in fact, there's some great research from Stephanie Archibald from Cylance that basically goes through how you would do this, and we're actually in the process of incorporating this into the payload as well. What about portable executables Windows? Oh God, there's so many ways to inject these, and actually it's really easy. Basically, you can create a DLL that contains your shellcode or contains your interpreter. you can basically inject it in so many different ways. And Dave Kennedy went through a few of those, talking about Unicorn and then the different ways of doing encoding. So yeah, it's kind of a rich tapestry. I just did like a search of methods for injecting shellcode into Windows, and these are all screenshots I found out. So we got you covered there. What about the rest of the payload? Well, obviously, you don't write payload in sort of a complex, stack-oriented, assembly way. What else do you do to make it easy to target to a lot of different environments and a lot of different operating systems? Well, one thing is to use boring libraries. Don't write things yourself. If you can find something off the shelf that just works, just use it. The great thing about that, too, is that it becomes less signaturable, less fingerprintable. If you're just using curl versus like some custom HTTP client you used, it's just going to look like curl on the wire. It's just going to look like curl in your process image. Silence is going to say, hey, it's curl, it's whitelisted. So there's a lot of benefits to just using normal, boring stuff. Also, we use AutoMake and AutoTools. I don't know if any of you guys have ever used AutoMake or AutoTools or LibTool. Anyone here? No? If you've ever done /configure, you've used it, all right? Maybe you didn't have to write anything for it. You didn't write any M4 scripts. And I saw someone shoot himself in the head. That's perfectly warranted. But I'll have to admit, I actually like AutoTools. Mostly because it just makes, if you've ever tried to do cross-compilation with anything else, it's still a pain in the ass. So it's the least worst thing that we have today. Talking about some libraries and things that we used to actually build this sort of universal payload. One of them was libev, libio. So to make it so that we can scale and have a lot of different functionality inside of a single payload, we want to make sure that basically all the different pieces of it don't step on each other's toes. Potentially, the way Meterpreter works is you can actually have, a lot of different things going on simultaneously. You might have like a dozen different tunnels going through it at once. You might have commands coming from actually multiple Metasploit frameworks. I don't know if you guys knew this, but actually a single Meterpreter can actually talk to multiple frameworks simultaneously. Nothing we've really ever exposed, but it's something we use during development here just to make sure we'll be able to scale properly. We evaluated a few different event libraries that allowed us to basically do this kind of scaling. We chose libev not because it was our first choice. We basically built some code around libevent and found that it was too big. So kind of like this would be a sort of a three bears sort of scenario. We built some code around libuv and found that anytime you ran on a kernel that didn't have every feature it needed, it would blow up in segfault. So libuv is the basis of Node.js. Libevent is all over the place. Libuv is basically kind of a little bit of an underdog. You actually have to download it over CVS to get a hold of it. But it actually turns out it's really, really good. It's very small, very compatible, and it runs on Windows, OS X, Solaris, HPX, IRIX, pretty much everything you want. And it's just pretty awesome. Now, to make it easier for you guys, if you ever want to use libev or libio in your own programs, I actually have it forked onto GitHub as well. So there you go. libdnet. This is sort of kind of something I carry with me everywhere I go. Doug Song wrote it probably about 2004 was the last update. But actually, a lot of projects use it. If you ever look inside the source code of Nmap, it actually has an embedded copy of libdnet. And libdnet basically lets you do all kinds of interesting networking stuff from a very small library, maybe like 50K of code, 50K bytes of code. And so you can do things like packet captures, you can do routing, you can do ARPing, you can do all sorts of cool stuff. And so again, I've got a fork of it if you guys are interested in using the more up-to-date version of libdnet. Cigar is a really cool tool as well. One of the neat things about it is it lets you basically do all kinds of interrogation of the operating system, yet it's still completely whitelisted in a lot of scenarios. And the reason why is because it's actually built into a lot of commercial monitoring agents. This is sort of, everyone's got their own fork, but they all basically work the same way. So, the usage patterns, were the way it looks for things, the way it determines if you're in a sandbox, the way it determines if you're inside a container, the way it checks what Linux version you're on, it looks just like the New Relic agent. So if you use Cigar, you not only save yourself having to write a lot of code for introspecting systems, but it also basically makes it look completely legitimate. Actually, I've worked with developers at BMC that use it in their own agent. And again, I've got a fork here with some extra improvements for Metal built on top of it, make it work on Windows more easily and that sort of thing. But again, using boring tools not only saves you time, but also makes your payload just look very normal. For SSL, Windows Meterpreter, Linux Meterpreter used OpenSSL. And I know you guys love OpenSSL, right? I can see a lot of OpenSSL fans out here in the audience. But of course, aside from the pain it is to build OpenSSL, it's very, very big. In fact, if you were to look at Meterpreter today and you see it loading the initial like 900K, per stage, 700K of it is OpenSSL. We're hoping to get rid of it at some point, but at the moment that's where it is. But for this new payload, we use Embed TLS, which is from ARM. They luckily open sourced it under, I believe, a Apache license after a lot of GPL commercial sort of weirdness, and it's pretty awesome. You can get basically a full TLS stack in about 100 kilobytes. And of course, curl. I like curl. Curl gets a lot of hate because hey, it's written in C and that sort of thing, but it supports so much stuff, and it's been through a lot of hell and back, and it works with all the weird things: chunking, encryption, verification, version negotiation, MIME types, proxies, all this stuff you get for free. Don't write your own HTTP client, just use curl. It's easy. And the other great thing about curl is, and a lot of people don't realize it actually has a ridiculous number of other protocols it supports. You can use Gopher or FTP or IMAP. You can use TFTP. You can do SSH over curl. You can do Telnet. You can do SMB over curl. It's pretty ridiculous the amount of stuff you can do over curl. And we actually have it all turned off right now, but soon it's going to be turned on, and we'll be able to do lots of interesting stuff with Meterpreter. The payload itself, how do we sort of build it? Like I said, we use Automake. It's kind of a little bit of a learning curve, maybe a lot of a learning curve, but definitely worth it if you're cross-compiling things that have to work everywhere. That's basically kind of the nuts and bolts of it. I used a lot of LibreSSL and OpenBSD code in it as well. And so this is what our system detection code looks like. So basically, everything can automatically fall back to built-in internal defaults. So like if you don't have a particular string mechanism or you don't have a particular C library function, it automatically detects everything and substitutes in the right compatibility layers as needed. Again, just took straight out of LibreSSL, jammed it in here. I know there were some C coders in the house. I want to show you a little bit of something interesting. Here's how you can basically write portable C code that basically papers over the weirdness between different operating systems. In this particular case, we have a file called limits.h. Limits.h usually contains things like what your max path is, or how big a page size is, something like that. So how do you use limits portably across lots of different operating systems? Well, one way, of course, would be that in your C code, you can just have a bunch of different kind of includes for different operating systems. Or you can insert a shim header that basically intercepts all your other header includes and replaces them with its own. So here's a little neat C trick down here. You see this include next. Now this doesn't get highlighted by Vim, but it turns out it's actually implemented in almost every C compiler except for Visual Studio. But what it basically does is it looks for the next path in the search environment, and it includes the next place where we might find limits.h. So you can basically put this magical limits.h early in your search path, and then it will automatically include the second one. There's a crazy trick you can do inside of Visual Studio as well, where you basically add a relative path jump, and this will cause it to basically do the exact same thing because it looks like a different file, even though it's literally the same file. So you're basically tricking it into thinking that it should actually look for this other file to include. Unfortunately, kind of annoyingly, between Visual Studio 2013 and 2015, Microsoft decided that rather than putting the include files in a directory called include, they changed it to UCRT. So you have to have this one little tweak to make it work. But the nice thing about this now is once you have this set of headers built, you can basically write code just that assumes that everything is normal, and it gets basically a normal environment built around it. Something else that we do to make things easy to extend and easy to port to a lot of different operating systems, we work on a lot of different operating systems, is we use conditional compilation. So rather than using a lot of if-defs and a lot of, if it's Windows, do this, if it's not, do that, we actually, inside the build system, automatically choose which sources we're going to build automatically. So we can see here for OS X, we automatically pull in the OS X clipboard stuff. If it's any kind of Apple device, we'll pull in the webcam, so that means we can also grab the webcam from a Mac or an iOS device. If it's Linux, it pulls in the Linux webcam version. There's Windows variations, that sort of thing. It just makes it really easy to just add functionality without having to do a lot of sort of twisty, windy code like I showed earlier with all the if-defs. Another way we keep code sane is we actually write object-oriented C. I know, well, C doesn't really have objects, but what you can do is basically you want to hide everything from everything else. So if you create these opaque structures and you never actually tell anyone what's inside them, you can effectively create every function and treat it like a method instead. And that allows you to basically hide internal implementation details and then reuse code across different boundaries, and you don't have all this sort of kind of spaghetti mess that all C programs turn into. Here are kind of some examples about how easy it is to add functionality that works across all the different platforms. Here's what the code that gets the current working directory looks like inside of this new payload, this new Meterpreter payload. And very much all you have to do is register a function pointer for get the working directory. You say what it should be looking for inside the incoming method stream. And then the system will automatically dispatch a context to that handler. You do whatever it is, get the path of the file or whatever it is you need to do. You create a response and you return it. The system is pretty nice in that there are other ways you can return as well. This scenario works really well for cases where you want to return right away and you don't think it'll actually take any time to return because there's basically an event loop that's handling all this. That way, if you have something that might take a long time, like for instance here's code that calculates the SHA-1 of a file system, of a file. You can actually create a custom event handler that basically runs in the background. There's a magical thread pool that automatically gets instantiated for every OS and can deal with managing each asynchronous operation as it runs, and it'll actually keep you from doing too many simultaneously so you don't use too much resources. There's a lot of really cool stuff going on underneath the covers. And then you probably can't see this, but effectively inside your callback, you can then generate the same kind of response and then return it asynchronously. And if you guys want to go into this a little bit more detail, I can definitely do that. Now, not everything's sort of joy and roses. When it comes down to testing and implementing these sort of things, a lot of times you run into weird stuff that you never expected. I actually had this bug reported on Twitter, which was everything works fine except on ARMv5, like an actual ARMv5 box. So actually, let's see. The problem, of course, was that I didn't have one. So I got this little Zip It device from 2004. It's a little text messenger from for kids, so they can basically text their friends. It turns out it runs Linux, and you can just pop a little SD card over here and replace the whole OS with your own. So I put Debian on it and managed to reproduce the bug. So the question is, do you see what the bug here would be that would only affect one OS architecture and not any others? The basic problem here was that every time it would run through this loop, it would say that the packet was bad and would free the packet and return null. You guys see where the bug might be? I know it's kind of quick to take a look at it. So it turns out that some CPUs, if you just point a structure to an arbitrary memory offset, it ignores that address and just chooses 4-byte alignment instead. So effectively, it was ignoring the pointers that we're giving it and instead just using whatever it decided. And that's actually a pretty common problem when you develop for kind of older CPUs that don't support byte alignment. So of course, you have to do things like adding packed attributes and that sort of thing. But all in all, there's not really a whole lot that we've had to do other than sort of some little odd tweaks on the side that make this work pretty much everywhere. Pulling it all together, other sort of important pieces to building sort of a universal payload. One is makefiles. If you guys like makefiles, you'll love these makefiles. They're the best makefiles. But in order to keep it kind of manageable, we made a different makefile for every subsystem that we have. So it can be built independently, tested independently, and more importantly, it's not a 1,000-line mess. Instead, everything's just in maybe a couple dozen lines. Another cool thing we have is automated testing. So here we actually have a lab full of routers, and someday we should actually show some pictures of what our big lab full of routers and different devices looks like. But effectively, we can now run automatic exploit testing and make sure that we can inject payloads into them and make sure that they always consistently work. So this allows us to tweak the payloads and the exploits and make sure that we're not breaking everything, unlike my first month at Rapid7 when I broke the whole tree. So here you can actually see running an exploit called the Moon, which is basically a command, or it's actually a buffer overflow, but it's very reliable, and running on a couple different Linksys routers and then verifying that it works. And of course, the final project is that anytime we do a build, we can actually automatically publish all the payloads out to Ruby gems and then incorporate it into Metasploit. Today, the project actually supports, I think, 11 different CPU architectures and at least 4 different operating systems. And we're looking to support more directly. Another kind of neat sort of bit of catharsis that came from this project was getting to delete the old code. Remember I showed that there were 600,000 lines of code in Windows Meterpreter? We were able to delete 234,000 lines of code just last week as a result of pushing in this new implementation. So sometimes, even though you add more, you actually end up with less. This gives you kind of an idea of all the different architectures that we're actually targeting right now. If you run Metasploit today, you'll see ARM64, big and little endian ARM, MIPS, 64-bit, different 32-bit variations, a lot of different PowerPC, and yes, even ZArch. ZArch is basically the CPU that IBM mainframes are based on. So you can run Meterpreter on a mainframe. Other things, here's actually it running on Windows. It actually has some pretty cool stuff where when you generate a binary, it can be reconfigured on the fly. So, for instance, here I had generated a metal payload, or I'm sorry, I should have mentioned this before, but this universal payload is codenamed metal. For like, it's got a lot of metal, a lot of moxie. So here, for instance, is running as a background process in Linux or in Windows. Here's another instance of it running as an iOS application. It can run both as a library and as a standalone executable. So if you want to actually embed it into a project, you can easily do that and basically work on it just like it's sort of an object-oriented piece of code. What's next? Well, one thing that we're working on, and I've had a lot of interest from various people, is how do we get payloads that can jump between Windows subsystem for Linux and Windows. There are a lot of interesting sort of escapes to go back and forth between the environments, but we're experimenting with using Windows subsystem for Linux as a way to basically hide a payload within a Windows environment. And so basically, when you look at processes, you won't see it in the normal way as a Windows process. There's some interesting stuff there where Windows subsystem for Linux is actually more strict than Linux itself. One of the interesting things we found immediately was that the mmap command in Windows subsystem for Linux can't deal with invalid flags. And Linux technically shouldn't either, but of course they always want to make sure that they never break their ABI. So there's probably some interesting opportunity for fuzzing. Other things that we're looking at, I've been working a little bit with Big Endian Smalls on how to get this working on the POSIX subsystem for ZOS. Right now when we target mainframes, we target the Linux partitions, but we can actually potentially run this on native ZOS as well, which would be pretty cool. We're also looking at basically taking the same magical toolchain that we have that we use for injecting the payload and using it to do all the interesting local privilege escalations that have come out for Linux kernel over the past decades. One of the biggest problems we have with Linux local privilege escalations is targeting all the different architectures and operating systems and C libraries. In fact, if you use Metasploit and try to use any of the privilege escalations for Linux, a lot of times they actually try to build code using the system compiler. Obviously not a really great scenario, so we're looking at basically making it so that we can have universal binaries we can inject everywhere for privilege escalation. Of course, fileless macOS injection is really nice. Because the payload's so new, nothing really detects it anyway, but it's always nice to have that sort of scenario. Something else that we built into the payload from the beginning was we didn't always intend for it to just be Meterpreter. We can actually give it different personalities and have it talk different languages out, different protocols out. So we're actually working with the Routersploit project to incorporate it there as well. So this would not only be a Meterpreter, but it actually could run against Routersploit and give you different kinds of shells in that sort of scenario. Some lessons that we learned from building this. One, you have to have a need. I worked on this for probably a year and a half without really knowing why I needed it. And when it came down to like, well, actually, we need it for this kind of exploitation, it's useful here and there, then suddenly the project really took off and we actually made some real progress on it. But you really have to have a need to sort of build these sort of things. Obviously, not reinventing the wheel is generally good advice, but in the case of building exploitation tools, it's even better because it makes your tools look more normal and basically work more normally. And you save a lot of time as well. We spend a lot of time fixing existing stuff, but sometimes just making things new is the best way to go. And of course, like I said, normal is better than clever any day. Now, for demos, I sort of broke all my demos here. I do have a whole bunch of cool gear, but I had some networking issues at the last minute, as you might expect. I can actually show you guys what it looks like to sort of develop the payload. But before that, maybe I could take some questions if you guys had any. All right. Yeah. The amount of Perl? Yeah, well, that actually, a lot of that comes from the AutoConf build system. So, yeah, it's pretty funny. Yeah, Metasploit was originally written in Perl, as you might remember, and so I don't think any of that's actually from that original bit of code. But yeah, there's actually not a lot of Ruby in it either. Surprisingly enough, that's mostly just the library code that's required to just link it into Metasploit. It has a bunch of basically just a binary generator at that point. So it doesn't take a whole lot of code to do that. All right. Well, if you guys want to ever get into developing for this, you can actually check it out from GitHub Rapid7/Metal. And I'll show you a little bit about what it's like to basically to build it and install it and test it. So the first thing you want to do when you check out the source code is not a whole lot. Pretty much all you have to do is check it out and type make. You of course want to make sure you have a C compiler or something like that installed. But even if you don't, I can actually show you the README file real quick. We have a lot of targets sort of built in by default that make it really easy to just get started. For instance, all these targets up here are built-in Linux targets. The system will automatically download cross-compilers for you. We bootstrapped them already for OS X, for Linux. We have a universal Linux toolchain, and for Windows. So you can actually target Linux from Windows. You can build these payloads on Windows. I like to build them on OS X just because, hey, I've got a Mac right here. Other things to kind of note is that you can also target Windows really easily using the MinGW toolchain. It's very easy to install on most Linux systems, and I've got it also here on my Mac too through the Mac Homebrew. If you want to target iOS or any of the other kind of systems, Android can also be targeted natively. Basically, all you have to do is figure out what your host tuple is, and it will just automatically build it. So I'm going to give you guys a demonstration of what the build process looks like. All the build files actually get built into a build directory. So if you want to clean up your project, all you have to do is just delete the directory. There's really nothing else you have to do. And then all you have to do is type make. It'll actually build everything from scratch. And of course, there's maybe a few warnings here and there, especially for OS X. But it builds really, really quickly. I'll go ahead and start another terminal up here real quick. Give you an idea how to test it. So you can see it's building curl. Curl is the longest part to build of the whole process. And basically what it's doing under the covers here, in case you want to see, is it's actually writing stuff to a log. Mostly all the boring stuff just gets piped away, so you don't have to watch it. To build out log files. So if you want something to watch while you're waiting, you can definitely just tail the build file. You can actually build all your architecture simultaneously. So if you like to use up all your battery or really get your fans spinning, you can build for 20 different architectures all at the same time, and it'll just work. While that's going, I'll go ahead and get Metasploit going. We have something really cool in Metasploit called the multi-payload. And actually, I'll just get started and I'll show you what this does. So for the purpose of testing and evaluating, a lot of times you have to get the right architecture, the right operating system, everything for Meterpreter. But we added last year a special payload called Payload, multi, Meterpreter, reverse, HTTPS. And what this guy does is pretty cool. Oops, let's see, did I type it wrong? Let's see. There we go. Not sure how I typed that differently. But basically what this is, it's kind of a cool magical payload that automatically does the right thing for any particular incoming connection. So we've got that guy. And if I were to set my host to, I don't know, loopback. So now we've got a handler listening. We're just about done building. All right, we're done. Build, Darwin, bin, metal. It actually has a friendly help screen, so you can actually reconfigure it on the fly without having to go through MSF Venom, which saves a lot of time for debugs. You can turn on debug and set it to a debug level, maybe 2. You can set a URI as well. Let's do HTTPS. Page 443. You can write all the output to a file. You can run it in the background. You can automatically install persistence as well. Lots of interesting stuff. So here we go. Oops, develop platform. Let's see. Let's switch this real quick. There we go. Oh, shoot, I know I did wrong. Here, just a second. TCP. There we go. All right, so anyway, that was just a quick demonstration of getting the payload up and running for debug purposes. Over here you can see it actually kind of merrily spitting out all kinds of different output over here. And then here we've got a shell on a OSX box. Here's PS. Here is LS. Let's see. Webcam, list, snapshot. There we go. So, all right, that's it. Thanks, guys.